All right, hello everybody. We're going to look at lesson 7 today, which talks about the probability of mutually versus non-mutually exclusive events. So we're going to talk in a minute about what that means to be mutually exclusive versus non-mutually exclusive. But before we do, we're just going to go through these few situations and just kind of discuss whether or not these events, event A and B, could happen at the same time. Okay, so here's the experiment or the trial. Number 1, you toss a coin. Event A is you get a heads. Event B is you get a tails. Well, that can't happen at the same time. You can't get both a heads and a tails at the same time. So this is going to get an X. Whoops, I got to turn on my pen. Whoops, sorry guys. There we go. All right, that's better. So this one's going to get an X. Okay? All right, you roll a 6-sided die once. Event A, you roll a 1. Event B, you roll a 6. Well, you can't land on a 6 and a 1 at the same time, so this also gets an X. Okay? Trial 3. You roll a 6-sided die once. Event A, you roll a 2. Event B, you roll an even number. Well, if you want to roll an even number, there are 3 outcomes that would be favorable to that event. Landing on a 2, a 4, or a 6. So if you were to land on a 2, that would actually satisfy both event A and B. So these could both happen at the same time. This gets a check. All right. Number 4, a bag contains 2 yellow and 3 blue balls. 1 ball is drawn from it. Event A is a yellow ball is drawn, and event B is a blue ball is drawn. All right, well, you can't draw both colors at the same time, so this gets an X. 1 student is selected as the classroom monitor. Event A, John is selected. Event B, Kate is selected. If you're only selecting 1 student, you can't select John and Kate at the same time. So this is going to get an X. All right. 2 more. Number 6, a card is drawn from a deck of standard playing cards. Event A, a spade is drawn. Event B, a heart is drawn. Okay, well, if you know about playing cards, 52 cards in a deck, they're divided into 4 different suits. One of the suits is spades, one of the suits is hearts. You can't draw a card from 2 different suits at the same time, so this is an X. Okay, and finally, a card is drawn from a deck of standard playing cards. Event A, a heart is drawn, and event B, a king is drawn. Well, this could happen at the same time because the card, the king of hearts, if you were to draw that card, it would actually satisfy both events. It would be a heart and it would be a king. So this could happen at these 2 events could happen at the same time. Okay, so mutually exclusive events, and I like to just abbreviate this as ME because I hate writing it out over and over again, are events that cannot occur at the same time. Okay, so we've seen lots of examples in this little exercise that we just did of 2 things that can't happen at the same time. If we were to come up with another one, let's say we're rolling a die. Okay, and event A is, you roll an even number. And event B is that you roll an odd number. Okay, well, you can't roll an even number and an odd number at the same time. So those two events would be mutually exclusive. Okay, on the other hand, non-mutually exclusive events, and I'll abbreviate this as non-ME, are events that can occur at the same time. Okay, so let's say, for example, we're rolling a die. Okay, and let's say event A is rolling an even number. And event B is rolling a prime number. Well, if you look at the outcomes that would be favorable to event A, and when I say rolling a die, by the way, unless I say otherwise, I'm talking about a standard 6-sided die, because you can get these fancy dies that have 9 sides and 12 sides and all sorts of stuff, and I actually have some of them at home. But if I don't say otherwise, assume it's a 6-sided die. Okay, if you roll an even number on a 6-sided die, well, the favorable outcomes would be 2, 4, or 6. Okay, now prime numbers are numbers that have exactly 2 factors. Okay, so if you think about what are the prime numbers on the faces of a 6-sided die, well, the sample space is 1, 2, 3, 4, 5, and 6. Okay, so let's just go through this. 1 isn't prime because it only has 1 factor, and a prime number has to have exactly 2 factors. 2 is prime because it has 2 factors, 1 and 2. 3 is prime because it has 2 factors, 1 and 3. 4 is not prime. It's got 3 factors, 1, 2, and 4. 5 is prime because it's got 2 factors, 1 and 5. And then 6 is not prime because it's got more than 2 factors, 1, 2, 3, and 6. So this is the set of prime numbers that you could get on a 6-sided die. Now, the outcome of 2 actually satisfies both event A and event B. So if you were to roll the number 2, then that's actually favorable to both events, meaning that event A and event B are not mutually exclusive. Okay? So let's go through a couple of questions together. Okay, in each case, state if the 2 events are mutually exclusive or non, and justify your answer. So justifying your answer, by the way, is either showing something in the sample space to say why, or you could provide an example as to why. Okay, so tossing a 6-sided die and getting a multiple of 4 or a prime number. Well, if we look at the multiples of 4 on a 6-sided die, this is just 4. And this would be, we just came up with those, 2, 3, and 5. So these are mutually exclusive because you can't have both of these happen at the same time, right? There's no common outcomes to both events. So these are mutually exclusive. Okay? Tossing a 6-sided die and getting a number that's a factor of 2 or a prime number. So our prime numbers again are 2, 3, and 5. Our factors of 2, a factor of 2 is a number that 2 can be divided by. So that would be 1 and 2. And we've got this number 2 that satisfies both events. So this is not mutually exclusive or non-mutually exclusive. All right, choosing a chocolate bar. The bar contains raisins or the bar contains nuts. Well, think about this. Could a chocolate bar contain both? Well, when I was a child, my mom's favorite chocolate bar, and it still is, was Cadbury's Fruit and Nut. And that has raisins and nuts in it. So this is not mutually exclusive, right? The chocolate bar could have both. Right? So example, Cadbury's fruit and nut. It's funny. I like this chocolate bar now a lot more than I did as a kid. Okay, so why are we talking about this? Well, it's important when we're calculating probability or the probability of two events occurring to think about whether they are mutually exclusive or not first. Okay, so if we wanted to know what's the probability of this event or this event happening, or what's the probability of this event and this event happening? So now we're looking at what's the probability of two events? Well, if we're going to do that, we need to know first whether or not they're mutually exclusive or not. So that's why we're discussing this now. Okay, now on a Venn diagram, this is coming back to Unit 2, LR2, which we've just looked at. If the two events are mutually exclusive, meaning they can't happen at the same time, there's not going to be any overlap, okay? These are also called disjoint, okay? If they are mutually exclusive, okay, that means the probability of both of them happening, PA and B. Remember, this is an intersection. Right? And you can think of the word and. What's the probability that A and B happen? Well, it's 0 because there's no overlap in the outcomes. Okay, so that's like if one of them is getting an even number and one of them is getting an odd number, what's the probability that you roll an even number and an odd number? It's 0 because you can't roll an even number and an odd number at the same time, right? Here's another example. If you toss a 6-sided die once, what's the probability that you're going to get a 4 and a 5? You can't land on two numbers at the same time. So that would be 0. On the other hand, if you're looking at the union, what's the probability of landing on, of A or B? Then you just add the two, right? We would just add these two together. It would be this plus this. Okay, so what's the probability of getting a 4 or a 5? Well, you'd have to say, well, what's the probability of getting a 4? It's 1/6. Plus, what's the probability of getting a 5? It's also 1/6. So altogether, that's 2/6, which reduces to 1/3. Okay? When things are not mutually exclusive, then there's going to be some overlap because they are going to share some common elements. Okay, so the two events will share common outcomes. Overlap. Okay, so if we want to know, for example, what's the probability of A or B, right? A or B is like we're joining these two together. And remember, or is a union. So we use this sort of elongated U to show that it's a union. Well, that's going to be the probability of A plus the probability of B, but then we have to subtract the overlap because otherwise we're going to count it twice. If you think of this as A, and then this is B, but then there's this overlap. Well, now we've counted the overlap twice, and we should really only count it once. So we have to subtract the probability of A and B, which is the intersection. So we're going to subtract this little piece. Okay, now if you were to say this out loud, you would say the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. Okay? Or you could say minus the overlap. All right, so let's look at some examples. Now, and one thing I should say actually before we move on to some examples is that this formula is great to use if you don't have the ability to actually write the sample space out or draw a Venn diagram. But if you can either write out the sample space or draw a Venn diagram, I personally find that strategy much, much easier. Okay, so we're going to look at all sorts of examples right now, but we'll see some examples where we can solve it by writing out sample space, by drawing a Venn diagram, by using a Venn diagram, and then finally we'll look at some situations where we might have to rely on this formula to be able to solve a problem. And this formula, by the way, any formula, has a bunch of unknowns in it, right? So this one has 4 different potential variables. And as long as you know 3 out of 4, you can find the 4th. So that's how we might have to end up using it. Okay? All right. Let's look at this guy. All right, so here we have a Venn diagram of, I suppose, people have been surveyed about what flavor they like. Maybe this is cake, maybe it's ice cream, maybe it's pudding, I don't know. But there's a chocolate flavor, there's a vanilla flavor. Okay, first question, are the events vanilla and chocolate mutually exclusive? Well, we can see from the Venn diagram that there's people who like both. So the answer to this is no. Okay, now what is the probability that a randomly selected person likes only vanilla ice cream? Well, remember, probability is the number of favorable over total. We don't have the total yet, but we can get the total by adding up all the different regions of the Venn diagram. So the total here is going to be 8 plus 12 plus 9 plus 3. And that works out to be 8 plus 12 is 20, plus 9 is 29, plus 3 is 32. Okay, so the probability of only vanilla is the section of the Venn diagram that's vanilla but not chocolate. So that's 9. So the probability of only vanilla is 9 over the total, which is 32. Okay, what's the probability that a randomly selected person does not like vanilla ice cream? Well, not vanilla is everything outside of vanilla. So how many people do not like vanilla? That's the 8 people who only like chocolate, plus the 3 people who like nothing. So probability of not vanilla is 8 plus 3 over 32, or 11 over 32. And these probabilities, you can leave them as a reduced fraction, or if you want, you could convert them into a decimal. And typically with these probabilities, we round decimals to the nearest hundredth. All right. So I'm going to do one more on the next page, just to do with this first Venn diagram. And then I'll let you guys try the second one yourself. Okay, so here's another one. Are the events even and odd mutually exclusive? Well, firstly, even if we didn't have a Venn diagram in front of us, we should all know that even and odd is mutually exclusive because you can't have a number that's even and odd at the same time. So yes, you can't be even and odd at the same time. Okay, what's the probability that a randomly chosen number is even? Well, to figure out if it's what the probability is if it's even, you've got to figure out how many different numbers are in my sample space. It looks like there's 9 altogether because the numbers go from 1 to 9, and there's none that are outside of these two subsets, even and odd. So the probability of even is, well, there's 4 even numbers out of 9 altogether. Okay, what's the probability that a randomly chosen number is even or odd? Well, the probability of even or odd, we would just add the two probabilities together. And there's no overlap here, so we don't have to worry about subtracting an overlap because we're not going to be double counting anything. So even is 4 over 9 plus odd is 5 over 9, which is 9 over 9, which is 1. Okay, and what's the probability that a number is even and odd? Well, we just talked about this. You can't be even and odd at the same time, so this probability is 0. All right, I'm going to let you guys try the next one on your own, and I'm going to skip to an example on the next page. Okay, so here's another one. The probability of a team winning its game, event A, is 0.42. The probability of the team not winning its game, event B, is 0.2. Okay, determine the probability of A and B and the probability of A or B. Well, to do this, we have to think about, are these mutually exclusive or not? Can you win and lose at the same time? And the answer to that is no. You can't win and lose at the same time. So A and B are mutually exclusive, okay? You can't win and lose at the same time. Okay, so what does that mean? Well, what's the probability of P, A, and B? What's the probability that they both happen? They can't both happen. So the probability that they both happen is 0. What's the probability of A or B? Well, if they're mutually exclusive, then we just add their two probabilities together because remember, there's not going to be any overlap. So we're not double counting anything. So this is going to be the probability of A plus the probability of B. And that works out to be 0.42 plus 0.2, which is 0.62. Okay. Okay, so we're going to try a couple of these practice questions, and then we'll move on. A 12-sided die is rolled once. What's the probability that the number rolled is less than 3 or greater than 9? All right, well, let's think about what would be favorable to less than 3. If we call that event A, Less than 3 would be the numbers 1 or 2. Okay. Greater than 9, if that's event B, on a 12-sided die, that would be 10, 11, or 12. Okay. If we're looking at what's the probability of A or B here, now these are mutually exclusive. We can see very clearly because we've written out the sample space, there's no common outcomes between these two events. So the probability of A or B is just the sum of their two individual probabilities. Okay, so that's here. If there's a 12-sided die, the probability of getting a 1 or a 2 is 2 over 12, that's PA, plus number greater than 9, there's 3 numbers greater than 9, so 3 over 12. So altogether, that is 5 over 12. Okay. All right, number 2, a pair of dice is rolled. What's the probability that the sum of the numbers rolled is either 8 or 12? Okay, so these types of questions come up quite a bit. And the idea here is that you have a pair of die and you're doing something with the outcome of the two numbers. And oftentimes you're either taking the sum, which means you're adding, in this case, or you'll also get questions sometimes where you're taking the product, meaning you multiply the two faces together. Okay, now to figure out what types of outcomes would that lead to, because really you're taking two faces and creating one outcome with it. And the one outcome is the sum of the two faces. The best way to organize the results is into a table like this, right? So along the top, you might put, what could I get on the first die? And along the side, you might put, what could I get in the second die? And then in here, what we're gonna do is, well, what would the sum be, right? So in this box, if I get a 1 and a 1, my sum would be 2. If I get a 1 and a 2, my sum would be 3. If I get a 1 and a 3, my sum would be 4. And I'm just gonna keep going. So this would be 5, 6, 7. Okay, if I get a 1 and a 2, this would be 3, 2 and a 2 would be 4, 2 and a 3 would be 5. So this kind of creates a pattern, 6, 7, 8. This is going to be 4, 5, 6, 7, 8, 9. And then this is 5, 6, 7, 8, 9, 10. 1 and 5 is 6, 7, 8, 9, 10, 11. And then 1 and 6 is 7, 8, 9, 10, 11, 12. Okay, now if you look at how many different outcomes are there, well, this is like there's 6 in each row, and there's 1, 2, 3, 4, 5, 6 rows. So there's 36 outcomes altogether. Okay, if you circle how many of them are 8 or 12, I'm going to circle them. Well, here are all my 8s, and here's my 12. So let's see, we've got 1, 2, 3, 4, 5, 6. 6 of them are either an 8 or a 12. So the probability of getting an 8 or 12 is 6 over 36, and that reduces to 1/6. Okay. All right. I'm going to skip the next one because it's very similar to question 1, and that's one that you guys can try yourself. And now what we're going to do on the next page is one where we actually have to incorporate something that we did in the previous unit, which was set theory. Okay, so 16 people study French and 21 study Spanish. Altogether, there are 30 people who study either French or Spanish. A, are the events study French and study Spanish mutually exclusive? Justify. All right, so how are we going to justify? We're going to justify with a Venn diagram. All right, so let's go. Here's my Venn diagram. And I've got people who study French and Spanish. Actually, I shouldn't draw the bubbles yet because I don't know whether they're going to overlap or not. All right, let's think about this. There's 16 people who study French and 21 who study Spanish. If I think about the number of responses altogether, 16 plus 21, that's 37. But there were only 30 people who study either or. So the number of people is 30. That means 7 people answered both. Okay, so it is a case of overlap. There we go. All right, so one of these is French, one of these is Spanish, and there's 7 people in the overlap. Now to figure out the rest of the diagram, well, my French circle has to add up to 16. So 7 plus what is 16? 7 plus 9 is 16. So this has to be 9. Okay, and then 21 people study Spanish. So 7 plus what is 21? The missing number here is 14. 7 plus 14 equal 21. And then just to make sure that you've done things correctly, make sure that the total is 30, right? So 9 plus 7 plus 14, that does in fact add up to 30. So that's good. Okay. And we are not told in this situation that people don't study anything. So nobody goes on the outside. All right, so what is the probability now that someone studies French? Well, there are altogether 16 people that study French out of 30 total. So the probability that someone studies French is 16 over 30. Right? And you could reduce that to 8 over 15. What's the probability that someone studies Spanish? Well, that's 21 over 30 because 21 people study Spanish. And you could reduce that to 7 over 10. And again, if you wanted to answer these as decimals, that would be okay too. Okay. What's the probability that someone studies French only? Well, French only is the 9, and this is where the Venn diagram is really important. If you didn't have this Venn diagram, it'd be really hard to see that that was only 9. Okay, so this is 9 over 30, and that reduces to 3 over 10. Probability that someone studies Spanish only is 14 over 30, which reduces to 7 over 15. What's the probability that someone studies French and Spanish? So French and Spanish is the overlap. That's 7 over 30. And what's the probability that someone studies French or Spanish? So French or Spanish is the union of those two subsets. So that means we have to add all 3 of those numbers together. So that's 9 plus 7 plus 14 over 30. And that's just 30 over 30, which is 1, because nobody is on the outside in this case. Okay, so I'm going to leave you guys with the one on page 64 to do. It's quite similar to the one that we just did, and I'm going to move on to this one on page 65. Okay. A school newspaper published the results of a recent survey. This is about the eating habits of students. 62% skip breakfast, 24% skip lunch, and 22% eat both breakfast and lunch. Okay, well, what's tricky about this one, right? If you think about it, well, what would go into our Venn diagram in terms of the subsets? One of them would be skip breakfast. One of them would be skip lunch. If you eat both, that's the same as skipping neither. If you eat both, you don't skip breakfast and you don't skip lunch. So this 22%, those are the people on the outside. Okay. Now, the other thing that's kind of interesting about this one is what's our total here? If the survey results are given to us in terms of percentages, that means that the total in our Venn diagram has to add up to 100. Okay? So if we think about, firstly, we know the 22 is going to go out here. Okay? If we think about the percent answered, and we add those up, we've got 62 plus 24 plus 22. And that adds up to 108%. That's more than 100%. Our total has to be 100%. Okay, that means that this is non-mutually exclusive. So I actually jumped the gun and drew this Venn diagram with overlap, but I did that correctly because 8% actually skip both. So this has to be 8. Okay, and our two bubbles here are skip breakfast and skip lunch. And then the 22 on the outside are the people who eat both. That means they skip neither. Okay, now if 62% skip breakfast, and I've already accounted for 8 of them, well, 62 minus 8 is 54. So this would be 54 because altogether now that adds up to 62. And then for lunch, right, it has to add up to 24. 8 plus what is 24? This is 16. Okay, so for part B, determine the probability that a randomly selected student skips breakfast, but not lunch. So that's only breakfast. All right, so the probability, of only skips breakfast is going to be 54 over the total, which is 100, or 0.54. Okay? C, determine the probability that a randomly selected student skips at least one of breakfast or lunch. So at least one of means they skip breakfast or lunch or both. So that's actually the union of skips breakfast and skips lunch. Okay, so that probability is going to be, we have to add up 54 plus 8 plus 16 over 100. Because the 54 is only skips breakfast, the 16 is only skips lunch, and the 8 is skips both. And that works out to be 78 over 100, or 0.78. Okay. All right. So I think we'll do this one too. Okay. Standard 6-sided die is rolled once. Event A is rolling an even number. Event B is rolling a multiple of 3. So let's just write out those outcomes. Event A would be even, so 2, 4, 6. event B is ruling a multiple of 3. Multiples of 3 are 3 and 6. Okay. Are these mutually exclusive? Well, could they both happen at the same time? They could, because you could roll a 6. So these are non-mutually exclusive. Okay. And that's since 6 is even and a multiple of 3. Okay, well, what's the probability of A? The probability of A is 3 out of 6 because there's 3 even numbers out of 6 total, which is a half. Probability of B is 2 out of 6 because there's 2 multiples of 3 out of 6 total, so that's 1/3. Okay, now what's the probability of A and B? Well, the only thing that satisfies both is 6, so that's 1 out of 6 because there's only one outcome that's favorable to both. And what's the probability of P of A or B? Well, if you think about what that could be, right? Now, the common mistake that people make here is they add 3/6 and 2/6. Okay? The problem is there, though, that if you did that, you would be counting this outcome of 6 twice because it belongs to both of them. So you've got to be very careful with these non-mutually exclusive events. And what you actually want to do is think about what is A or B. What works for that? It could be 2, 3, 4, or 6. You could get any of those results and that would work, right? So that would be 4/6, which is 2/3. Okay, if you added 2/6 plus 3/6, you're adding this outcome of 6 twice. And so you're double counting it. So a better strategy is to actually explicitly write this out so that you don't overcount it. All right, what we're going to talk about now is what happens if you actually don't have sample spaces or a Venn diagram to work with. What if we just have to use the formulas? Okay, so if we just have to use the formulas, then what we need to remember is that if we have mutually exclusive events, the probability of A or B is equal to the sum of the two probabilities. Okay, and if the events are non-mutually exclusive, then the probability of A or B is equal to the probability of A plus the probability of B minus the overlap, minus the probability of A intersection B, right? And we're subtracting that so that we don't count it twice. Now, these two formulas are on your formula sheet, so you don't need to memorize them. But the idea here is that we may have problems where we're given all but one unknown, and so we can fill in what we know into these formulas and solve for the unknowns. Okay, so we're going to go through 2 examples of that, and then that'll be the end of this lesson. Okay, in a particular class, students either walk to school or are given a ride. If the probability of being given a ride is 0.68, and the probability of walking or being given a ride is 1, determine the probability that a student walks to school. Okay, now on a particular day, you can't walk and being given a ride at the same time. Okay, so these are mutually exclusive for a particular day. Okay, so what does that mean? If you're either walking or being given a ride, right? If it's only one of those two, then the sum of the probabilities has to add up to 1. because if it's either or, you must be doing one of those two, right? So if the probability of being given a ride is 0.68, and the probability of walk or ride is 1, right? Well, let's think about this, right? P walk or ride is equal to P walk plus P ride. That's where that formula that we just went over comes in. So if we fill in what we know the P walk or ride is 1. That equals the probability of walking we don't know, plus the probability of being given a ride is 0.68. Well, now we can solve for P walking, right? We just have to subtract 0.68 from both sides, and we end up with the probability of walking is 0.32. Okay? All right. We're going to do one more, and then we will call it a day. And in fact, I'm going to skip this one, and I'm going to do this one over here, number 2. Okay? So, probability that a student passes Math 30-2 is 2/3. Okay? So I'm going to write that out, actually, off to the side. So let's just say the probability of passing math is 2/3. And the probability that he passes English 30-1 is 4/9. So passing English is 4/9. If the probability that he will pass math or English, so that's pass math or English, is 4/5, what's the probability that he will pass both subjects? So passing both subjects would be what's the probability that he's going to pass math and English? That's what we're looking for. Okay? Now, if you think about it, these are not mutually exclusive. You could, and hopefully you do, pass math and English at the same time. That's what you would want, hopefully. Okay, so let's actually write out our formula. The probability of math, and in fact, instead of writing the union and the intersection, I'm just gonna write or and. Or English is equal to the probability of math plus the probability of English minus the probability of math and English. Okay, so now I'll fill in what I know. Probability of math or English is 4/5 equals probability of math is 2/3 plus 4/9 minus the probability of math and English. Okay, now we just need to solve for what we don't know, right? Maybe what I'll do is I'll subtract 2/3 and 4/9 from both sides. Okay, so this side is just going to be negative the probability of math and English. And this side is going to be 4/5 minus 2/3 minus 4/9. Okay, now what I'm going to do is I'm actually going to go and use my calculator now to do this, because we can answer these as decimals if you want. And maybe I'll just do these fractions on my calculator. And I'm using my iPad right now, so I'll use the one on my iPad. Whoops, there it is. Okay, so it's 4/5 minus 2/3 minus 4/9 equals, and I get negative 0.31. Okay, so I'm just going to continue over here. Negative 0.31 equals negative P math and English. What does that mean? Positive 0.31 is the probability of passing math and English. Okay, so that would be how you would use these probability formulas if you don't actually have the ability to draw a Venn diagram or write out the sample space. Okay, so I'm going to leave it at there, and I will see you guys